Hello everyone, myself Dr. Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to the today's session on volume integral, which comes under the concept of vector integration. Today, I am going to introduce the volume integral and how to evaluate the volume integral, and also some problems on volume integral. A volume integral is the generalization of a triple integral f of x, y, z, dx, dy, dz. So here we have triple integral. That means we need to integrate three times. One with respect to x, then with respect to y, then with respect to z. So we need to find the limits of x, y, and then z. Let V be the volume bounded by a surface and f bar of r bar be a vector point function which is defined over V. Then the volume integral of f bar in the region V is denoted by volume integral f bar dV is triple integral f bar dx, dy, dz. For example, if this f bar is given in component form f1 I bar plus f2 j bar plus f3 k bar, then evaluation of volume integral of this f bar is to evaluate the triple integral of each component. So I bar into triple integral of f1 dv plus j bar into triple integral of f2 dv plus k bar into triple integral of f3 dv. So evaluation of a triple integral of a vector means simply to evaluate the triple integral of each and every component of that vector. And also here f bar dv means the triple integral f bar dx, dy, dz. That means we need to find the limits. We have to integrate with respect to three variables x, y, z. So we need to find the limits also. What is x? X varies from, y varies from, z varies from. So in general, the main point is to consider the limits as one variable in terms of the remaining two variables, then second in terms of the third in terms of the constant. That means, for example, here in general, the z limits, we find the limits of z in terms of the remaining two variables f1 xy to f2 xy. And now y, already z is over. Now the remaining is x. So y changes from g1x to g2x and x changes from constants a to b. So if one of the limits are constants, then we can obtain the numerical solution or numerical answer of the given volume integral. So in general, we consider the limits in this way. It's not compulsory to follow the same order. If you want, you can consider y limits in terms of remaining two, f1 of x comma z to f2 of x comma z, then x limits in terms of z, g1z to g2z, and finally z limits in terms of constants c to d. Or else you can start with x, then y, then z. So the main point is in the evaluation of triple integral, we find the limits of first variable in terms of remaining two and limits of second variable in terms of the third and the limits of third variable in terms of constant. So this is the procedure to consider or to identify the limits of z, limits of a triple integral. Let us solve one problem of finding volume integral. So a vector f bar is given. Evaluate volume integral f bar dv, where V is the region bounded by the surfaces. So here x equal to 0, x equal to 2, which indicates x varies from 0 to 2, y 0, y 6. So y changes from 0 to 6, and z is given in terms of variable z equal to x square and z equal to 4. So z changes from x square to 4. So therefore, given f bar is 2xz I bar minus xj bar plus y square k bar. Now volume integral f bar dv means the volume integral of each component 2xz over v dv minus j bar into x dv over v plus y square k bar into volume integral y square dv. And here given limits x changes from 0 to 2, y from 0 to 6 and z from x square to 4. Since z limits are given in terms of x, we start with integration with respect to z. So here this is same as I bar into triple integral 2I bar. So xz dz first, then y, then x, minus j bar into triple integral x dz dy dx plus k bar into triple integral y square dz dy dx. Coming to the first integral, we need to evaluate the triple integral xz dz dy dx, which is the x limits are from 0 to 2, then y limits from 0 to 6, z limits from x square to 4, xz dz first, then dy, then dx. So which is x from 0 to 2, y from 0 to 6, x constant, integral z, which is z square by 2, 0 to the limits are x square to 4, dy dx, which is x from 0 to 2, y from 0 to 6, x into, so upper limit is 4, so 4 square 16 by 2 minus lower limit x power 4 by 2 dy dx. So that's equal to 1 by 2 we can write outside, integral from 0 to 2, y from 0 to 6, this is 16x minus x power 5 dy then dx, which is equal to half into x from 0 to 2. Now integrate with respect to y. So with respect to y, 16x is constant, so we get integral dy is y minus x power 5 into y dx, where y from 0 to 6. So half into 0 to 2, 16 into 16x into y is 6 minus x power 5 into 6. So dx. So half into x from 0 to 2, 96x minus 6x power 5. So we need to integrate this. Half into 96x square by 2 minus 6x power 6 by 6 from 0 to 2. So this is half into 48 into x square is 4 minus these two gets cancelled. So this is 64. So again by multiplying with 1 by 2, so this becomes 24 into 4, 96 minus this is 32. So which results as 64. So the first volume integral is 64. Similarly, we need to find the second. So integral, triple integral x dz dy dx, which is x from 0 to 2, y from 0 to 6, z from x square to, so these are the limits, x dz dy dx. So x from 0 to 2, y from 0 to 6, integral dz, since x is constant, integral dz is z from x square to 4. So the first integral is over, with respect to z is over. Now with respect to y we need to integrate. So upper limit is 4, lower limit is x square. Overall it's a function of x. So while integrating with respect to y, we get 4x minus x cube into integral dy is y from 0 to 6. So which is integral x from 0 to 2, 4x minus x cube, upper limit is 6, that comes here. Now with respect to x, 4x square by 2 minus x power 4 by 4 from 0 to 2. So this is 2 times, and 2 square is 4. So 8 minus 16 by 4, 4. So 24. Similarly, we need to find the third one, y square. Also, triple integral y square dz dy dx is x from 0 to 2, y from 0 to 6, z from x square to 4, y square dz dy dx. Since the function is y square, while integrating with respect to z, we treat it as constant. So integral dz is z. X from 0 to 2, y from 0 to 6. So y square into z from x square to 4 dy dx. So with respect to x, with respect to z, the integration is over. Now x from 0 to 2, y from 0 to 6, y square into 4 minus x square dy. Now with respect to y, so this is constant 4 minus x square, and for this we get y cube by 3, 0 to 6, and hence after simplifying, here we get 4 minus x square into y cube, 6 into 36 by 3 dx. Since the upper limit is 6, 6 cube can be written as 6 into 6 square. So just for our convenience. And here x from 0 to 2, so this is 72, that comes out 4 minus x square dx with respect to x. So 4x minus x cube by 3, 0 to 2. Here the integration part is very simple, and we are using simple integral formulae such as integral x power n, integral sometimes sin x, cos x, sin theta, cos theta, etc., which is x power n plus 1 by n plus 1. So this is 72 into the upper limit 2, so 8 minus 8 by 3. So which is 72, 24 minus 8, 16. So here 24 into 16. So we get 384. And hence the volume integral is the combination of all these three. Hence the triple integral v f bar dv is equal to, so first one, how much we got? So 2 I bar into the first triple integral, 2 I bar into first one is 64 minus j bar into the second is 24 plus k bar into the third one is 384. So hence 128 I bar minus 24 j bar plus 384 k bar. So this is the volume integral of the given vector. So simply evaluation of volume integral of a given vector means to evaluate the triple integral just by integrating its components. So in today's session I have introduced the volume integration and solved one problem on volume integration. In the next class again we will solve one more problem on the same evaluation of volume integral. This is for today's session. Thank you.